Yeah, so I was asked, pick a paper that I loved, and this is a paper that I read maybe 6 months ago that I was pretty astonished by. For context, my background is in psychology, so I'm obviously not a language designer by PhD at least. And I've been involved a lot in the language Julia, which has sort of gotten me really interested in language design issues, but had no real formal training. And 6 months or so ago, I read this paper and was really sort of astonished at the simple sort of astonishing clarity of the paper, of just how much it covers with such simple language. Still obviously mathematical, and also just sort of how clearly this was like one person thinking this through, and was not sort of like just a regurgitation of what a bunch of other people had done, but was like this was actually one person's very personal perspective on languages. And part of what I like about the paper is that it's pretty clearly opinionated at a few points, even though he tries very hard not to be so opinionated. So for context, so actually this paper is sort of a misnomer in some sense, because actually what it is a set of lecture notes that were prepared for lectures that were given in 1967, and then the lecture notes just stayed in sort of secretive, unpublished form, but were actually sort of an open secret being passed around by many, many people all the way until 2000, when finally the paper as we know it now was published. But in the meantime, between 1967 and 2000, the world obviously changed quite a lot, and many of these ideas had disseminated very far by the time this paper was actually finally published. So I'm just going to go through literally section by section, so that sort of thinking of this as like a reading group, except that I am standing up in front of everyone rather than everyone sitting at a table. I'm going to go literally down by section. So the first section, just to give a sense, is a preliminary section. And so it's sort of a broader sort of philosophical discussion of why Strachey believes that the study of programming languages matters and why people need to think about it. And one of the very first parts is that it's just a simple introduction section where it sort of basically says, why do we need to think about these things? Well, we need to introduce a bunch of jargon and at least some formal terminology, because otherwise all the concepts that we use for programming are just so vague as to not be usable. And the obvious example that he gives, and this will come up later, is name. When I use name and you use name, are we talking about even vaguely the same thing? And especially at the time, given Algol 60, this was quite a complicated issue, because call by name meant something very different to Algol programmers than it meant to the rest of the world. And so that sort of starts it. Then it goes into a section that I really enjoy, but I find is kind of strange, which is sort of this philosophical preliminary section. And so it sort of talks about philosophical outlooks and how this informs the way that people think about this. Obviously, at this point, sort of everyone who's a computer scientist is really a mathematician still. There's sort of all people who maybe have a PhD in math. And so one of the very first things he starts talking about is constructivist and classical mathematics. And it's sort of weirdly, I find, opinionated take on this sort of surprisingly aggressively anti-classical mathematics. But I like the fact that he sort of very much articulates his aesthetic, and at the same time articulates an aesthetic that's unique to programming that actually has nothing to do with the philosophical points that he's talking about, which is one way why I say in this slide that in many ways this discussion seems slightly irrelevant to me, but interesting. Just to be I guess I ditched the discussion of constructivists. Yeah, if you don't know what constructivist mathematics, it's worth reading the Stanford Philosophy Encyclopedia article. It's quite long. It's a pretty subtle topic. Sort of one way to think about it is throwing out the law of excluded middle and seeing what you get after that. If you know what the law of excluded middle is, then think about what that means. If you don't, you probably won't find this topic very interesting. I'm actually personally pretty anti-constructivist, so it's interesting to read this take. But then he goes on and starts getting sort of much more about things that are actually about, well, I guess this last line is the last thing that will involve constructivists, which is this claim that I find sort of strangely strong, given that I don't think I agree with it, is that he sort of unquestionably sides with constructivists and says basically those who require construction rules are the ones who have rigor, everyone else is just not. I'm not really sure why this comes up, but it does. Moving on though, I think there are actually starting to be really interesting things about sort of philosophical perspective. And one is a philosophy about language that I really like, which is this notion that actually the crux of thinking about programming language should be concerned almost exclusively about semantics. But thinking about syntax is interesting, but largely not very interesting. But the most interesting thing, particularly, is this phrase, explore the field of semantic possibilities. And I really like this, because I think in many ways, as I've grown as a programmer, a lot of it is just learning what is the field of semantic possibilities, what can languages offer, and the syntax is really, in my mind, sort of a much more trivial and uninteresting part of it. And then this claim, which I really like, this is part of what I like about this paper, sort of how personal it is. This notion that we're still at the point in time comparably to when calculus people were debating how big differentials were. Sort of, before they had realized that you actually could make the infinitesimal calculus work and actually not just be made up, there was a point at which they believed it, but they were doing it totally non-rigorously, and they were doing all these arguments about fluxions and other sort of nonsense, and sort of argument basically that at 1967 is where programming stood. That people were just using terms that sort of were probably irrelevant in the first place, and they were thinking about things in a totally wrong way. And then this part I love. And this actually, this first paragraph is one of the quotes that I most loved in this whole paper, because I think it sort of broadly applies to everything I interact with as a sort of mathematician of sorts, which is this notion that we need to be very, very cautious about what we decide to formalize, and particularly this phrase that ends this paragraph. We should not have any axiomatization without insight. I think is really awesome. I think lots of fields go very early on into axioms. Being a psychologist, the field I think of immediately is economics, which is sort of a field that went very heavily down axioms, and sometimes without a lot of insight into anything useful with the axioms. At the same time, I think, given if you're sort of a mathematician by disposition, you want this. And I think arguably the reason is this final sentence of this next, or the first sentence of this next paragraph, which is that making a point is also important to make sure we're not fake. So we need to make sure that we are being precise, but at the same time we should just avoid being precise or pointed precision. So then we start with section 2. And this is sort of where now you start to get into the guts of the paper, things about programming languages. One of the things I decided with this is that I would translate the examples into sort of pseudo-Julia code, which is sort of basically something like C code. I think it'll be actually pretty clear in a few points, which is basically all of the examples in the paper, if you haven't read it, are all in this language CPL. I have no idea if CPL has ever actually been used by anyone other than the people in this group. But CPL has a few pieces of notation that were extremely vague to me when I first saw them, particularly things involving right arrows and down arrows. And my decision was that sort of I had so little ability to introspect into the right arrows that I decided to replace them with what they were in Julia. So you'll notice this in a second. So the very first thing is the very first place in which you start to talk about computers is the thing that's different from all of what mathematics had been talked to about up until that point. It's really there's just sort of is no math about this concept. If you have computers, where just suddenly you have an abstract store, it has memory, and you can overwrite it. And this is just not a thing that people were talking about when they were talking about math. And suddenly, how did you deal with this? And assignment statements are the way that we now tend to think about these things. And so you give some basic examples. And part of this interest of giving a basic example is to sort of, one, highlight how this is different from simple mathematics, and then also realize why these examples are a little too superficial and maybe lead you down the wrong routes. And so one is just saying I'm going to have some variable x, and then give it a single scalar value. Then I have another thing like a variable x, but I'm assigning a scalar value derived from another one. And then the last one is where you actually have the idea that you actually have a store where things get overridden, which is you are actually assigning a value to x that is dependent on its previous value. And the mere fact that you could do this actually suddenly means that sort of all of the things you have about intuitions about math are suddenly gone. Like certainly if this was an actual equality sign, this means nothing. So how do you think about this? But what he points is that actually this makes things a little too easy. Like reasoning about those first few assignment expressions are a little too simple. One is that you don't think about things like what happens if you have a complicated expression. So here I've used a bunch of ternary operators. This is the replacement for this right arrows in CPL that I found kind of opaque. And so one is, we're assigning something, but what we're assigning is conditional. So the actual value that winds up going into y depends on some computation. And then you start getting into more interesting things, like assigning into elements of arrays. And so now you're getting into things that are specific stores, but are sub-stores of them, and how you choose which of them. Then finally, this last example is actually not valid Julia. I tried for a while to figure out if you could make a version that looks like this and runs. I couldn't come up with any version of this that would actually run and would look like this, which is, we have a left-hand side, we evaluate the left-hand side, and then we figure out which of the variable names we're going to assign to. I couldn't quite come up with a version of this that would actually run this way. Obviously, we could do conditional different types of assignments where we have different assignments depending on the condition. But I couldn't come up with one where the left-hand side is exclusively about either picking J or K as the name. But then sort of having shown you the sort of reasons to think that things are complicated, then we get onto this topic of saying, well, the general form looks like this. We have some expression on the left, we have some expression on the right. We want to put the thing on the right and to the left. And when you see it like this, it becomes very obvious the terminology that gets introduced. And this is, to my knowledge, really first introduced in these lecture notes, though now we use these terms quite a lot, which is the introduction of L values and R values. And there's the things that are on the left-hand side that are location-like, and the things on the right-hand side that are value-like, and how we decide to do what we decide to do with them. And I think, it's really kind of awesome to see this material presented in its first light because it's quite clear. These paragraphs, I think, are sort of totally unambiguous about why you would use these terms L values and R values. And they sort of lay it out very nicely. One thing that's sort of subtle if you haven't read the paper is that, Strachey goes to a point to emphasize that this is not just a pointer, that the L value is some location that may or may not be as simple as a single address of memory. And part of the reason for this is emphasized that there's actually going to be a section later on in the paper about pointers. And so it's worth sort of distinguishing early on between L values and pointers. Obviously, they're sort of similar, but are not identical. Then there starts to be this. This section is about definitions of variables. I have a little struggle trying to come up with examples. I'm sure that there exist languages in which the second thing on this slide exists, but I couldn't come up with one. So the first one I think we all know about, which is having some initial declaration of a variable, where I say, here's some new L value, P. Let me put some R value into it, like 3.5. That I think is pretty obvious to most people who've done programming. The next one I think is a little weirder, which is this introduction of a systematic alias. So I just invented notation for this. In the paper, there's like a squiggly equal sign that's being used here. But the notion I find really subtle, and the example, which is great, that's included in the paper, I think really gets at it, which is, suppose that I have I is 2, then I do this aliasing operation, x is MII, now I change I. What is x? And particularly, like, is x still referring to M22, or does it refer to something else? Here you're getting actually the L value of MII, but that is being put into x. And I couldn't quite figure out how to do this in sort of a language like Julia. There may be a construction that I was blanking on. But I think it's sort of an interesting concept. It's not clear to me how much one buys by these aliases, other than they're sort of just nice notationally. But it's a sort of an interesting concept. Name. So now we get onto this topic of name, and the first example of language that Strachey says is just sort of too vague to be useful. Basically what this section describes is what we would now tend to call an identifier. But part of the reason that it's given a section at all is to make clear that this distinguishes this from call by name, which algo uses. And I'll describe that in a second. There's actually like a really awesome footnote later on describing call by name, where he basically either invents or constructs the idea of a func. So that will come up in a bit. And then numerals. So then this obviously is like really simple to everyone, which is we have numbers that are written out. They can potentially be written out on different bases. So I might have a decimal base number, I might have a binary number, whatever. And there's this sort of cute terminology of calling this microsyntax. So sort of having this first level syntactical analysis, which parses the sort of microsyntax to turn things into numbers. Not too difficult. Then we have this conceptual model. So this is now the conceptual model of how L values and R values work in this abstract store. So we can have boxes, contents of boxes, and then arrows relating them. So we've got this figure. And so we've got things like names, so A and B, which then go linked out into boxes. So these are the L values. Inside of the L values, there are the associated R values. And those things point out to their specific values in the abstract world, like 17.3. Then we have just direct numerals. So these are things that are not L values, so there's no box involved. They just point directly to a value in the abstract space, and then we directly point out to a number. Then we have expressions. So we have things that are not L values, things that are R values, but are written in sort of complicated ways. And so here's a quite simple one. We're just doing some sort of multiplication. And then we have vectors, which is sort of the first place where things maybe get a little weird, because now we have an L value that is itself pointing to a bunch of other L values. So we have V, which points to a box, but that box itself points to a bunch of other boxes. So this is, I think, the first place where when I try to describe programming to someone who's never programmed before, I find this is sort of the first place where things get weird. There's sort of many L values. And then finally, commands. Commands is actually sort of a subtle issue, which is there's a very systematic distinction throughout this paper between expressions, which are completely pure and side effect free, and commands that are basically only side effects. but may depend on some expressions in order to operate. So there's things that change L values, and there are things that live only in the world of R values, and that's roughly the distinction of expressions and commands. So then we move on to section 3, which is the conceptual constructs. I've used the actual names of all these sections partly because I find the distinctions between the sections really opaque. I think the fact that this was clearly notes for a lecture rather than formal papers sometimes shows up, and one of them is why are the sections split the way they are? I have really no idea. So now this section is going to basically spend a bunch of time laying out definitions and making it clear that everyone has thought through how expressions and commands work and how they're different and how they think about them. So the first one is stuff that's probably pretty easy. So we have expressions, we have things like literal numbers, we have some operations on numbers that give numbers, and we have sort of more complicated chains of operations on numbers. But at the end of the day, all of these things just produce values. They may depend on the meanings that we have to associate with some of the symbols like x and y, but at the end of the day, we just get an R value. In contrast, a command is now when suddenly we're changing the contents of some L value. So now suddenly we're taking expressions, figuring out what their R values are, and then sticking them into the boxes that are these L values. And so these look basically exactly like the other thing, except now suddenly we have a bunch of assignments. So I think in modern terminology, and I don't really think this terminology really ever occurs in the paper, we tend to think of expressions as pure, commands as impure, but another way to say it is that expressions involve only R values, and commands involve at least one L value. And then one of the things that's going to come up over and over again is sort of part of the difficulty of programming and why you need to even have a theory in the first place is that basically all of math has given you only things for thinking about R values. That expressions exist in math world. As soon as you try to deal with commands, you suddenly are in this space that sort of math just has not dealt with previously. In languages, we actually find that sort of these things are pretty blurry. So here's a thing that is both an expression and a command in C. And I think people are not so obsessed with distinguishing these things. Strachey at a couple of different points sort of pretty heavy-handedly comes down against this, which I actually kind of like. It says don't chain these things all at once. Make sure you have expressions, then commands. Don't make it so that I have to reason about both of them at the same time, because otherwise I've made all the expressions just too hard to reason about. And then there's this, and I like this paragraph as well. So, to a large extent, you can think of the increasing power of these programming languages to increasing the size and complexity of the right-hand side of these assignment statements. And so I didn't excise the original version of sort of in this section of the text. There's a bunch of assembly code, and there's a translation into math. And sort of the gap in legibility between the assembly code and the math is pretty astonishing. The math is something we all grow up reasoning about and are really good at. The assembly code is much less enjoyable to read. And I think Strachey makes a really great point, which is sort of many ways, the ways that you make things richer are being able to put really crazy things on the right-hand side. And I think we actually still have ridiculously far to go in this direction. I think particularly I think a lot about things like vectorized math in languages like Julia or other languages. And how do we do this in a way that's clean and has coherent semantics? So I think we're really far from doing it in a good way yet. So I think we still have a long way to go in exactly this direction of increasing power by putting more complicated things on the right-hand side. So then we have sort of more detailed 3.2 section where we dive into expressions a bunch more. So the next thing is this notion that the most important definition of an expression is that it has a value, that every expression has some value, and particularly that it always actually generally really cares about the R value, but it has also an L value. And in this section, and he makes a point, we're just going to pretend that the L values don't matter. Let's just completely ignore all the L values and only focus on those R values. Let's think about only what the values are and not where we're going to store them or how we change anything. And this basically just this gives us functional programming. This gives us pure math, things that are easy to reason about using the tools we already have. And one of them, which is great, is the thing that I think lots of people don't, in my experience, think enough about programming is referential transparency. And sort of how much of a virtue is referential transparency, which is the notion that if I have many different expressions, the only thing I ultimately really need to know about those expressions when I'm evaluating them is their values. I don't actually care in any way about their surface form. I think it's quite easy to forget how important this can be. And so examples that we have are things like the following. So we have sine of 6, sine of 1 plus 5, and sine of 30 divided by 5. And if you have any math training, you immediately think of these things as being exactly the same. And the notion of sort of like you might actually need to think about the surface form in order to reason about this is something that I think most people would reject. But it is worth keeping in mind that sort of there have been many times in programming when people have explored things that did not satisfy referential transparency. You know, there are languages in widespread use today that also don't satisfy this. And sort of, you know, why do we do that, and to what extent should we be sort of trying to minimize that? And I think he doesn't really get really detailed into this, but to me, my mind, sort of the advocacy for referential transparency is both locality and ordered reasoning. So when I sort of don't need to reason about a bunch of other stuff, I can just reason about things in a simple order, which is first look at the sub-expression, figure out what its value is, and then I'm done. And then I never have to think about the complexity of how I got to that value. I just have the value and I'm done. And not being able to do that really sucks. And then there's this, which is, you know, in order to interpret expressions, we always have to think of them with reference to an environment, which provides the meaning of all the variables. You know, and this is, I think, like the first place. Well, like we've hit a bunch of places where I think, like, if you've never implemented a language, you probably still have a good intuition. And I think this is the first place where I think lots of people who haven't read a lot about programming languages and haven't actually thought about implementation often don't think about this, which is like, what is the environment that you're executing in? Where are you getting the meanings of these terms, and how are those things related? So there's this cute example, and I actually like don't know if this is the source of the where construction in Haskell, but you know, we've got this nice example of an expression which we have to evaluate with reference to an environment that defines the meaning of A. So we have, you know, some operation. And then we have the second expression, which again we evaluate with reference to A, but now A is defined in terms of B, and B we actually don't have any meaning for. So we're going to give some definitions for these terms in a second. You know, these two concepts are really important about thinking about expressions. And then, which I also like, you can see again this return to the I don't really care about syntax spirit that was started earlier in the paper, which is we see a bunch of other syntax versions. So we see let statements, and then we see lambda expressions. And the point that's made about these things is that they're all exactly the same. You know, you can pick one because you like the syntax of one, and that's cool. Strachey sort of over and over again says I don't really care about that. What I care about is thinking about the semantics. In particular, what I care about is thinking about A in those examples, which was a bound variable. A variable that, given the environments I already know about, I know what its value should have been, so it's been bound, versus things that are free variables, things that somehow have to derive their meaning from some context that currently has not been specified to me. And this actually gets a lot of like leverage out of this, including some stuff that I really like, which is going to come in a second. But first, then we start getting into talking about applicative structure. And if you're used to Lisp, this will be very familiar. This is basically just writing things out as S expressions. The syntax that he actually uses is this one, which is actually much more like, say, Julia would use in Lisp. But it's the same basic idea. We're just getting rid of all this infix stuff, and we're also trying to make sure that there's no precedence rules. So sort of no implicit precedence in the way we write expressions. Instead, everything is very clearly laid out in terms of its applicative structure. And one of the reasons you might like about this, as he points out, one of the things you might actually want to do is be reasoning about expressions in which the operators themselves are things that are being derived from more complicated expressions. And so the example he gives is one in which you have D, which is a differentiating operator, which given other operators produces their derivatives. So you can imagine applying, say, D to sine, then you know that that's going to give you cosine, and so you could have an expression that's like D of sine applied to some set of values that would replace or be exactly semantically equivalent to this. Then there's this sort of very simple definition of how evaluation works. And again, part of what I like about this paper is like if you've read structured interpretation of computer programs, you've seen all this stuff already. It's kind of awesome to like realize like, oh, I kind of cribbed that book out of this paper. So when it's like, I evaluate the operator, I evaluate the operands. And here's an interesting point that he really insists on, which is like not how I think of most programming languages, because most languages don't do this, which is we figure out the operator, we figure out the operands, we can do it in whatever order we want. Most languages are not like this. And then finally, we apply this operator to the operands. And part of the point of this is that we wind up getting a partial order out of things. Awesome. And the partial order, just to be clear, is this is the set of expressions I have to evaluate first, and then I can go downstream and evaluate other ones. And I think we actually really are still doing pretty bad about giving good languages for expressing this. Partly it's because most of the languages, at least that I know, have actually decided to make the order in which you evaluate things quite formal, and you can assume that you know exactly how it's going to happen, so you know like it's going to go left or right, for instance, when it evaluates all the operators and operands. And then also just, but broadly, yeah?
But the partial order also looks like a possibility of parallel.
Exactly, yeah, exactly. So that's why, that's what I think is kind of a bummer, is sort of languages have not done necessarily a good job of thinking about the partial order. Like, the language I most associate with partial orders is makefiles. Like, that's the thing that I like most think of, is like, I'm gonna articulate computation in terms of some DAG, and given that I know the DAG, everything that's at the sort of same level in the DAG can be done in parallel. This is like a really powerful formalism that I think, at least in my mind, I think we tend to way underutilize. And partly we really underutilize, given that we need to do so much more parallelism these days. I think we're like, it would be awesome if we had better stuff for this. There's probably a bunch of languages that I don't realize that do this, but this is one way I think of it. Then there's this nice aside where saying, all the expressions I gave you so far are pretty simple. You can do the evaluation rule I described, you're fine, except that this one. Once I have conditional operations, then no. This actually is slightly typoed out. I realized after I wrote it. This should be a double equals if it was in Julia. This is because I was translating all these arrow signs into Julia. I went a little fast, but the notion of like, what do I do? So I first check if x is 0, and then I either, if it is 0, evaluate to 0, or I evaluate to 1 over x. And the essential thing about this expression is that I actually need to not evaluate all the operators. So this previous claim of like, I evaluate the operator, I evaluate the operands, I do it in whatever order, that doesn't work here. So there's sort of this one aside. This section I decided not to dive too deep into, because it's sort of like a side that I find personally not very interesting about constructing ways of doing this without needing conditions. So sort of showing how you can get them out of lambda operations. I personally don't think that's super interesting, but if you read the paper, you're really interested in that. And how you deal with the fact that you need to have this conditional evaluation. Now this is the place where ordering starts to really matter. So before we had this nice partial ordering where like most things could be evaluated at a time, but some things had to be evaluated in order. Now we have commands, and now suddenly order is like ridiculously important, because the entire meaning of everything exclusively depends on the order, and if I change any order of anything, suddenly everything is broken. And so now we deal with commands and sequencing. And then I love this paragraph. This actually might be the best paragraph in the whole paper. So one important characteristic of mathematics is our habit of giving names to things. Curiously enough, mathematicians tend to call these things variables, and though their most important property is precisely that they don't vary. And this is like, this ridiculous thing. I have this interaction all the time where I was trying to describe programming to someone who doesn't know programming, and the first thing I think is like, well, I'm going to tell you what a variable is, but this is actually the first time in your life that ever someone is going to use this word in a way that's not stupid. Because I actually mean that it's variable, whereas everyone has always told you about things that are unknown, not variable. And so this is sort of this cute little aside that I love about talking about how variables work, and particularly how they interact with commands. You're going to see these sections get a little deeper, so there's going to be like a lot more quotes on the slides going forward. And then there's this awesome aside, again, of sort of the cost of doing this. The cost of doing this is introducing the idea of commands at all. Introducing the notion that I can be changing the values of L, changing the R values permanently in an L value. This is a huge problem. And, he just sets aside basically like side effects suck. We still haven't figured them out. He sort of says that he hopes that we're going to figure them out and clarify them. As far as I can tell, we haven't really succeeded. But it's like he at least hopes so. I've recently been reading a stats paper that's exactly like this, sort of like, I'm pretty confident 20 years from now things will be fixed. Like, no, they haven't been fixed. But it's fun to see a little optimism. Then there's this section about the abstract store. This is like one of these, so in the introduction, Strachey notes that there's sort of weird oscillation of hyperformalism and no formalism in the paper. This is a section that is sort of hyperformal. So we sort of define how commands work, and we define them in terms of these sigma operations. And sigma operations are basically that we have a symbol table. That's how I think of sigma standing for. It's the symbol table. So basically it says, you give me an L value like X, and I return, given sigma, I give you back its R value, because it right now happens to contain, say, 5. And then basically what happens is that you wind up having immutable symbol tables, and when you do commands, what you do is you wind up taking your old symbol table, sort of putting it somewhere where no one's going to use it again, but it doesn't get destroyed, and replacing it with a new symbol table, which contains the new values. So this is sort of how you think about commands. Yep?
How is that different than having stacked values?
How is it different from a stack of values? I don't think it is different from having a stack of values.
That was traditionally how compilers
Okay.
built something.
Yeah, I mean, I don't have a good feel for this session. So it may be that I've missed some subtlety in the way this section is presented. Like, the section strikes me as going way out of its way to make the symbol, the symbol table not mutable. But it's not clear that that's like just me being confused. But certainly I agree. So semantically, that's a good way to do it. I think almost every way would be better than making immutable symbol tables. But and then finally, there's this whole section about defining how commands work in terms of these symbol table operations. You know, like this is what a command is that it does this thing where it gives you one symbol table and gives you another symbol table. It's cool, it's nice. It's sort of one of the things that I find less sort of exciting, because to me this starts to strike me as sort of the axiomization without insight parts of the paper. Finally, we now go on to functions and routines. Functions and routines sort of very closely parallel expressions and commands, except they're now portable. So functions are expressions, but they're sort of nicely portable, and they let us change the bound variables, so we can sort of say things like f of x. Commands are also like this, except that now they're portable, but they're impure because they're routines, are commands. Lots of languages, that I think of used to care a lot about this distinction of, functions and routines. They don't seem to care about it anymore, which Strachey seems to be really upset about in this paper. And then there's sort of different notations. So here's just two different notations. And this actually is valid Julia code, but it's a lot like the code in the paper. One is where I have a named function that binds a variable x and then does evaluate some expression. Another whereas I have a name, an L value f, and I put into it an anonymous function. The point is that these things are effectively equivalent. In practice in, say, Julia, they're not exactly equivalent, but they should be at least. And then there's, this section. So this is a section where things start to get a little more complicated. So hopefully everyone's understood everything I've said so far. Hopefully everyone will understand this. But this is where things get a little weirder. So now we're thinking about is we have functions. We're going to pass them arguments. What do we pass? Do we pass the L values or do we pass the A values? This is like if you're used to pointers, this is exactly that. Like, am I giving you the actual thing? Am I giving you the value of things, or am I giving you a copy of the things, or am I giving you a way to reference the original thing? And so here's this exposition about you have to know whether each one of the bound variables is being provided as an R value or an L value. I think many of us are sort of familiar with different ways of thinking about this in terms of value or reference. And part of the reason that this is set aside is saying, either you get L values in or you get R values, is that there's also suddenly this other option which Algo 60 had. So this is the call by name that came up earlier. So, this paragraph is also awesome. So one of the things that makes languages difficult is that everyone does things differently. There's all these options here about what you could do for semantics, whether you pass L values and R values, and all of them do things differently. So if you know Fortran, you'll be familiar with the fact that Fortran only ever does everything by reference. So even scalars are being passed by reference, i.e. R values. In contrast, lots of things are being passed by value in Algol, except when things are being passed by name. It says call by value is like calling by R value above. Call by name is actually quite different. And there's this side about how things are complicated, and I'll now explain exactly how it works. So basically, if you read the paper, you'll notice there's a footnote to 3. You go like 40 pages in, and then you find out what 3 is. And 3 contains this. And I love this, because I, for a long time, had no idea what a thump was. And when I finally learned about it, it's pretty awesome. And so this is an implementation of how a call by name could be done. And so imagine that I have some procedure that's going to take in a formal parameter x by name. And so how would I implement pass by name? So one way that I might do it is that I would, every time I do this, create some new parameterless procedure, which takes in no parameters and evaluates out to the original expression A. And now what I can do is I can replace the original function f with a new function f prime, where every single time in its body it previously referred to x, which was going to be called by name. Now I replace it with this function. And this ability to call to evaluate this arbitrary expression. And now you can start to get sort of really weird things, because now you're passing in expressions that who knows what's going to happen. Particularly this would play sort of in very strange ways with potential with parallelism. So I like this a lot. This idea of constructing parameterless functions that let you evaluate expressions is what we sort of now generally would call a thump. So it's pretty awesome. This thing is like a little side note. Okay. Next, take a little water first. So this actually, my friend Adam is in the audience, will recognize that I recently put on my Facebook a share of a programming challenge in Python and Lua exactly about what's about to be said, and which is like, you thought it was bad that we were talking about passing L values and R values to functions. Well, what happens if we have closures? Now things get really wacky. And in fact, like, it amazes me because I think you can be an incredibly competent programmer and have just no idea how the language that you're used to programming and handles this. I think like it's just totally such a sort of subtle point that you might not ever think about. So let's talk about this super simple function. F of x is x plus a. Here's a closure. We've got a bound variable x, clearly specified by the environment of the formal parameters for this function. And then we've got a, this free variable. How is a going to be used? Well, one is that we might assume that a is being used by r value. In which case, when we do things, we wind up like this. A is 3, f of x now gets defined. It captures in a, what does it capture? It captures the r value, not the l value. So this means that I first evaluated on the argument 5, it's 8. I change the binding of a in the original environment, and then I call it again, and now I still get 8. This is captured by r value. I don't think almost any languages do this. I think Lua does that. I think that's the takeaway of that programming challenge that I shared. Yeah, this is pretty rare. I actually think this is awesome, and more languages should do this. So it's kind of part of what I like about this section is like, there's a lot to be said for making closures like this. They seem not to be generally. The other way you do it is that way you capture is not the r value, but the l value. And so now when you change a, suddenly now you change the meaning of this function. And this is, I think, how most people tend to think about closures. But you'll see in the section there's going to be a contrast with the concept of own variables, or what C would call static variables. In my mind, it sort of would have been better if one had chosen static variables to do this kind of thing. There are definitely use cases for this that I should make clear that there certainly is a useful thing. One thing that I find amazing is that, as far as I can tell, there has never been a popular programming language anyone has ever used in which closures allow you to choose whether you chose R values or L values. What's C++? C does? Yeah?
You have a choice. Yeah.
Oh, awesome. Oh, wow. Now you realize how deeply I don't know C++. Awesome. Thank you. Cool. C++ has it all. I always learn that every time, but I still don't know it. That's cool. Yeah, so there you go. So, well, oh, so OCaml, you have to choose the user ref in order to be able to get a no value? Cool, great. So people have thought about this. It's fun because this challenge is like, imagine I want to make a family of hash functions inside a function. How do I do that? And how do I make sure they're sort of like in a loop, say, and they're not all the same? All right, so then there's this own variable section. As far as I interpret it, this is basically like a static variable in a C function. So this is some value that's inside the function body, and yet it can persist in its value across calls. And so I tend to think of imitating this in terms of closures that capture by L value. So this is sort of how I would tend to implement it in, say, Julia, where I would make some f function, start with some initial value of I, and then have some ability to change I every time I call it. So this is some way you might try to imitate these own variables without actually having a formal construction that says, this is an own variable, or this is a static variable, or whatever. All right, now we have functions and routines, and thankfully it starts out by saying they're as different as expressions and commands, which is for sure true. And then here's the sort of rant. I sort of mentioned this earlier. It's really unfortunate that most programmers have decided to totally confuse these two. And this is certainly like the state of what I'm used to of all the modern programming languages have sort of doubled down on confusing the two. And so you have occasionally you can annotate things as pure, in which case they suddenly become straight piece functions again. Usually everything is sort of assumed to be a command. And then again, there's sort of this awesome sort of aside again about like how are we going to deal with side effects. And then sort of, it only gets worse because we've decided to confuse routines and functions. Yeah, and then this is the section which I also kind of love, because sort of again, sort of like, don't do that. Don't. You're already dealing with weird referential transparency problems. Really, like, try to avoid it. So if you're going to have some command and it's going to be no longer referentially transparent, break things apart. Sort of like, I love advocating this sort of often I find unpopular thing to tell people to write more code. But this is one approach, or make a comment, which is also kind of cute. Just like, every time you do something that's weird, you should tell people why it's weird. Here's a section. So this is actually one of the first sections where I have a little thing I'm not totally sure I understood in the paper, which is the meaning of hiding. I definitely understand this term freezing on the slide. I'm not sure that I actually figured out what hiding meant. Probably if I reread the section a few more times, I would have figured it out. So here's actually, but I like this section a lot. So here's a totally different way of thinking about how you're going to deal with side effects. Is instead of separating out functions and routines, pure and impure, instead one thing you might try to do is just talk about them in terms of the properties of the things being operated on. So one thing is you might say, well, I'm going to let you operate on these things, but now they're no longer actually changeable. And so now I've sort of solved these problems of mutation, but I haven't forced them on functions, instead I put them into data. And so one way you might solve it is hiding, which I'm not sure I understand. The other one is freezing, which I definitely am sure I understand. The freezing is essentially just what we would now think of as constants. So this is where I now. Yep.
I wonder how do you become like the Haskell does?
Maybe. I mean.
I think it's just you can encapsulate state function, so there's a state function.
Okay. Great. So there you go. Problem solved. Thank you. I was sort of counting on the audience to know some of the stuff I didn't understand. It's like a real reading group. It's awesome. Cool. That's awesome. So now I've only got a few more things that I don't fully understand that will come up later. So hopefully you'll fix those as well. So the characteristic thing about variables is that the R values associated with them can be changed. But one thing you might say is, no, I can't do that. So that's freezing. So this is the idea of constants. And this is interesting. This is down in the first place where we start talking about what are invariants and are they properties of L values and R values. This is going to come up again in a second in types. So here's where we're saying constancy is a thing about an L value, which is to say, this is an L value. It's a box. It can store things, but in fact, once I store one thing in it, it will never change ever again. And so here's the sort of first time when that concept comes up. And then now we talk about sort of the difficulties of what happens when you have the ability to actually mutate things. So one thing that's weird is that sort of now functions mean different things depending on what's going on around them. And so potentially probably pretty risky. And so then there's a nice distinction between functions in which there is actually nothing that's uncertain, and then there are functions in which there are some things that are uncertain, and here's the distinction between fixed and free. So a fixed one is which there's bindings, all the variables are bound. A free one is which none of the variables are bound. And then the question is sort of, can I move things in environments or not? And so the converse of a free function is a fixed function. And the crucial thing is that it's independent of its environment. So sort of what this thing is going to do, it's not a closure. It's going to do is very clear. You pass it its formal arguments, and now you know what's going on. And this is the first place where we start to actually talk about compilation, which is like the nice thing about working with fixed functions is that you can compile them, because they don't depend on things that maybe only exist at runtime. So then there's another section that reiterates this point by saying, talking about segmentation of programs, which is the nice thing about these fixed functions is you can compile them separately. And then there's a point which is, this is not the only thing that you can do. You can also make fixed functions that happen to create new free functions at runtime. That's also something that can be compiled separately. Now, this is awesome. So I would love, if anyone knows, I'm going to claim something which may or may not be true, which is that this is the first time I've ever think anyone used the term first class object. So this distinction of first class and second class, which is very popular nowadays in programming, I think starts in this paper. We're talking about the idea of are functions and routines first class or not? Can you pass them around to functions? Can you get them back as the results of functions? And you get, obviously super simple examples of this. Like, the first thing I can do, I can have some conditional, I can decide which are two values and then add to them, but I can't actually decide which are two values to apply conditional. There can't be any uncertainty about things because functions can't be the results of expressions, they have to be somehow literal in some way. And then there's an interesting point, which is like, now you've got sort of like this sort of historical or sort of psychological take on why this happened, which is that, probably the reason you wound up with this is that mathematicians assume that all of the names of functions are simple constants and are always recognizable. If you think that way, then you don't really think that there's any reason to make functions first-class citizens. So this is a claim about how you wind up with that scenario. And then there's a talk about how you actually represent a function. So like, what is the R value of a function? So up until now, we've basically implicitly been talking about all functions as L values, as things like sign that have sort of names of things that one does. What is actually the R value representation of them? And basically the way you do it is you make some closure, except that you also have another thing, which is a pointer to an environment containing all the free variables. The paper goes into more detail about this if you're interested. And then finally, well, no, not quite finally, we're still in section 3. This is sort of the last big section, and then section 4 is sort of a more sort of closing out section. So now we have types and polymorphism. And again, we're going to introduce a bunch of terminology for the first time. So we're going to talk about types and how functions interact with types. And I like this, because I always like, sort of get into constant debates with people about what types are. I think it's a very contentious topic. Sort of nice thing about thinking about like, what is the type of an object, and here's one definition from the CPL working papers. So, you know, a type is something that defines its representation and constrains the values of range of abstract values this could take on. And so, you know, this is like, I like to think of types often as sets of things that one possibly could have taken on for this L value. And the nice thing about this is that having made this assumption, having known something about the range of possible values you can store in this, now you can start to decide things about the representation. You can decide how much space you need to actually allocate to store this thing. So if you know like this thing that's always got 2 floating point numbers, then it only actually needs space for 2 floating point numbers. And then he points out, you know, in assembly language is basically the only thing that matters is size. That's all we really care about. The range is just bits, because they just store bits in it and they can do whatever. And now we get into this first definition of polymorphic. So we have operations whose meanings are ambiguous until you actually know the types of arguments. You know, because addition as an example. Like, what is addition? What exactly does it do? And this exact meaning actually depends on whether I'm adding integers, or floating point numbers, or floating point plus an integer, da 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 da. This is sort of polymorphism. And now there's a distinction between 2 types of polymorphism. But first we actually have to talk about manifest and latent. This is again, you know, so I brought this up in the constancy section, but it comes up again here, which is what things are attributes of L values, which things are attributes of R values. And the question is type which of them? Is type something that belongs to the L values, or is type something that belongs to the R values? And this is, he describes this distinction as manifest or latent. So it's manifest when the type is something associated with the L value, i.e. knowing the L value is completely sufficient, or it's latent when it's defined from the R value, and you actually might have to wait till runtime to figure out the type of things. And so there's a whole long section here about talking about how CPL decides to deal with this. And then I mostly like this in terms of thinking about, you know, this is all presented in the context of compilation, but it's all incredibly relevant. Like, you know, I know Wes here is a Julia person, and you know, anyone who's thought about Julia, this section will be very, very familiar to you. But thinking about, well, what really matters about thinking about polymorphism is when can I determine the types of the operations in order to figure out what the meaning of that operation even is? When does that actually happen? You know, in Julia, the way this works is basically you can compile things at runtime, because the time when you first call things, you actually know the values of all the arguments. And so this is, you know, for instance, how we figure out how A plus B should be reasoned about. And this, you know, the results of the rules he outlines are that you can figure out the types of every expressions at compile time, so it's easy to generate appropriate code. But actually, like, you know, we now know, you know, simple JIT systems like Julia can do this, you know, at runtime, because actually, like, when you finally first call a function, I now know the types of its arguments, and I can compile things.
Who is reasoning about the code here? Like coders or the compiler? Or
Here is primarily the compiler, though I guess I would argue that also there are benefits to the human. So I would tend to say that the human also finds the same code easier to reason about, because there's less uncertainty about what's coming in. But this is actually really a distinction at the compiler level. So this is the compiler's reasoning about, when do I know the types of these arguments? Yeah, but I do actually, you know, like, you know, the advocacy, for instance, of having like explicit types in Python 3, and sort of it seems like there may be some movement in that direction. I think that's more actually on the other side of like, there are also very good uses for just annotating types for humans to read. I've read a lot of like R code written by other people that's inscrutable for this reason, for instance. Or like, you know, is this a matrix? Is it a data frame? Who knows? So yeah, so we now know sort of, you know, this distinction is not necessarily required at compile runtime, because compile time is itself a term that can be kind of vague and change where it goes. And this is kind of awesome also. Like, you know, you can imagine a very different system, which is instead of knowing things at compile time, you can imagine that they're all properties of R values and they're all latent, and it sort of gives this awesome exposition of how you would do dynamic languages. And they're sort of like pretty awesome. The way this is sort of, you know, so the opposite extreme is also worth examining. We can imagine that only R values have types. They totally ditch them from L values. So now, like, you know, X doesn't have any type associated with it. Anything can go into X. But in contrast, every value has a specific type. And this is, most of what we now know from dynamic languages is this experience of like, every value carries around its type, and then it just winds up in different names, and the names don't care. And then there's an idea of hardware checking, which maybe happened at some point and I'm not aware of. I think this is certainly not the thing I think of as being happening nowadays about people checking types with hardware, but we do lots of type checking with strings. And then there's this idea, this is awesome about sort of introducing polymorphism, so we're going back now, is, let's be clear about things. The thing that was difficult about polymorphic functions is in no way solved by making things dynamic. Like this dynamic thing of latent types or manifest types, this doesn't solve the fact that A plus B is just a complicated thing. We have to think about it. And there are two ways we can basically think about it. One is we have what we'll call ad hoc polymorphism, a term, again, being introduced in this paper for the first time, but we now use a lot, which is basically, who knows? So basically, every time they give you a function, you just have to memorize how the types work. So there are no rules. It is literally ad hoc, which is, there's just something, you just accept it. In contrast, it distinguishes with parametric polymorphism, which is now that you have sort of very cleanly defined parametric families of functions. And this is a really awesome exposition of, say, how map would work. So imagine that I give you a function f. I know that it takes in arguments of type A, hands you back results of type B, and now I might, so you could write this sort of arrow type of A goes to B. I wish that second B was capitalized, but it's not. And then now what I have is L, some list, and I tell you all the elements of L are A's. So it's a list of type A. Well, now I might be able to talk about sort of applying a function to L. And this would be a parametric function, which is whatever the type of A is, I pass in A, and it is going to operate on lists. And given lists of A, will give me lists of feedback. And so here's sort of very nice, clean parametric specifications of how the type system works. So this. Yeah, this is totally independent of this. This is, yeah. Actually, to be honest, like, other than the fact that I think of this distinction as sort of like a meaningful distinction for one to learn to reason about, I actually don't have a good intuition for why one would care necessarily about this. The parametric one is nice in the sense that, like, I can give you more formal guarantees about how to reason about derived types and derived functions. So like here I'm deriving a new function from another function, and you can sort of easily reason about it. But it's not clear that this actually is that important to the compiler, like whether it's ad hoc or parametric. I mean, maybe it matters, and I'm just not aware of why it matters, but it's not clear that it matters that much.
Yeah, well, I suppose that you have the ability to do type instances, and you arguably have the ability to do correct.
Yeah, definitely.
So
So certainly, presumably, the more you use this, the more proof power you get. But you can still, but you also still get lots of, basically every ad hoc function you could think of as like, ad hoc polymorphic function you think of as like some axiom in your proof system. And then,
you talked about the difficulties of polymorphism. What's that referring to?
So the difference is like, what does plus mean? Like, how does the compiler, when the compiler sees plus, now it has to do a bunch of stuff. Because like plus might mean one operation when I'm adding ints, it might mean another thing when I'm adding floats. And so actually, like, whenever I'm going to figure out I'm going to say it really is polymorphic. Like, in terms of machine representation of functions, there are actually like n representations of functions that all get the name plus. And when I see plus, I don't yet know which of those representations I want to use until I know the types of the arguments. Maybe. I mean, it depends. It depends what you can prove at what time. So yeah, this is
just kind of a warning in a modern context. Parametric polymorphism is something different, and ad hoc polymorphism, especially if you talk about a lot of Haskell, is different than what it says there.
Interesting. What is it? Have I just these are verbatim quotes from the paper. Have I just misunderstood the quotes, or they just don't mean the same things anymore?
No, because when I say parametric polymorphism, right now it's like a Java generics, Scala, Haskell, where you define the list that takes a T, but if you don't fix the T, it works for any T.
Yeah, well, that's what this is as well. So this is saying this is implicitly defining the notion of, say, a map. And map is a function that, given an arrow type from A to B and arguments list A, will give me a list B back.
Yeah.
I mean, I certainly, this is not my field, so I would not be surprised if I had misused terms, but I think that we're actually talking about the same thing. But maybe maybe we'll catch up afterwards. I do believe we're actually saying the same thing. Cool. So we're actually like almost done. So we'll get to that conversation real fast. So this is nice, which is the type of a function. This is actually like my main complaint about Julia as a language is actually that I think that the type system for functions sucks. It is hopefully going to get fixed pretty soon. Jeff, who's the main compiler writer, has been talking about this in his thesis, which is just being handed in. So hopefully he's actually going to implement the stuff he talked about. But basically, like the type should be this. It should depend on the types and the modes of calling of all the parameters. Since in general, Julia, for instance, is a language that doesn't actually let you choose the modes of calling. That's not optional. Basically, all it has is the types of the inputs. The types of the inputs and the types of the results both matter. So that so you get a real arrow type. You get inputs of type A, outputs of type B. Then there's this aside about having this idea of variadic functions, which is just functions that take in variable numbers of arguments. So maybe this thing takes in 2 arguments, maybe it takes in 3, who knows? And you can say, this is an extreme version of polymorphism, where I don't even know how many arguments this thing takes until I see where it's been called. Let's see. Yeah, I'm actually going to skip this thing. It's an interesting point, and I've thought a lot about this, but I don't have a clear enough thing to say to make this paragraph useful to other people. So, compound data structures. So there's like this fun thing about saying like at the time of 1967, languages did not have a lot of data structures built in. And so there's this awesome quote about sort of like until mathematicians started doing things that were not numeric, i.e., artificial intelligence, they didn't even realize they wanted something other than an array. And then suddenly, once I started doing things that were other than that, it's sort of like, oh, data structures are cool. So this is sort of like this Lisp invented data structures worldview, and taking it out of atoms and cons. Then there's a sort of explanation of how one could invent how to build up types out of things called nodes and elements. This is one of the places I'm a little fuzzy. I think I understand the section, but I'm not totally sure, which is the idea sort of nodes are new entities in the type system that have no uncertainty about exactly what they are, whereas elements are entities in the type system that have uncertainty. Sort of things like maybe I'm a scalar or maybe I'm a doublet. So that's like one thing of the entry and say like the second part of a cons. But this is one of the things I'm a little weak on.
That is correct.
Sweet, thank you. Man, this is an awesome. Okay, so then there's this like sort of pretty obvious point, but sort of worth making clear, which is like in order to think about how assignment works in compound data structure, we actually really need to know exactly how L values and R values work for all the nodes and all their components. So if I want to talk about like some 5-element struct, or let's not call it 5, let's call it 5-node struct in order to deal with this element meaning in this paper. If we have some 5-node struct in our language, we need to think about what the R values are for each of those fields and what the L values are and how we reason about them. And then there's this like fun section about implementation, which is like got all sorts of crazy pointer hacks. I actually think that there are a bunch of languages that do this, like OCaml, that like play with bits in the pointers to decide what their types are. But this is like a pretty sort of much more technical and sort of not clear as generally applicable section. But it's cool. Let's see. So then there's this programming example section. So this section I sort of don't find that interesting. Probably just misunderstood why it matters, which is sort of just like going through and giving you an example of using all the concepts that were introduced up until that point. And so there's a data structure, there's some operations on it. Yeah, it's cool. Then there's this fun aside about pointers, which I really like, and particularly like, given there was like this whole point about like L values are not pointers, don't confuse the two. Now let's talk about pointers, and then which is like there's no reason why an R value couldn't be the way of referencing a location. And so what do we need? We need 2 primitive operations. We need follow and we need pointer. So basically follow is like given a pointer, I want to figure out what its R value actually should have been, and given some L value, I should be able to take an R value, which is the pointer to it. So I can take L values, give pointers, and then follow them back to get the actual R value back. So this is sort of the primitive elements that we know about. And if you're used to C or something like that, these will be pretty obvious how to translate them. There's some crazy notation for this in CPL, like down-facing arrow and up-facing arrow. Then fun side structures. I have no idea why he picked these structures, but it's kind of awesome. So there's lists, sort of arbitrarily long arrays that maybe grow. N tuples, fixed sized arrays that definitely don't grow. Sets. This is awesome because the paper is like sets are really hard. We're now totally used to it. It's like, oh man, this thing has like who knows, and it's got no order. And then we've got bags, which is like, another thing that's also really hard, but is sort of super important if you maybe care about, say, relational data. And then there's the section 4, which is like really is miscellaneous topics. So one, there's this idea of this formal exposition of load update pairs, which is really just an exposition of how you should think about L values and R values, which is like there are load things, which given an L value takes the load out, and there's an update, which is how do I change the content of this L value. And that's the load update pair. And then there's this final aside on macro generators, which I love. This is kind of like a super dig of a bunch of people. So there's sort of a much more conventional way of thinking about programs is just that they're just strings of symbols. And this is like totally the way that, like, say, I think of how I read like Gödel Bach by Douglas Hofstadter. He like constantly advocates this perspective of like they're just symbols, don't worry about it, the semantics don't matter. And what you might do is like you might imagine just like playing around with the symbols, and this is exactly how macros work. And one thing you might do is that you might want it within macro generator, which is like the way that you decide to manipulate programs is I give you some symbols, I play some beams, and I give you other symbols, and I don't worry about semantics. And I didn't quote it, he's pretty anti-macros. I'm a person who sort of finds macros useful in many contexts, but he sort of, it's very clear, like, hey, I should have quoted it. Something like, the future of programming languages will be improved insofar as we remove macros. And then I'm going to skip the section. So the last section is sort of like an extremely shallow and therefore not sufficient for me to even really understand introduction to possible ways you might try to formalize the semantics of programming languages. There are like 3 bullet points that say like, here's one approach, here's another approach, here's another approach. It says like, I sort of identify with a third of these. I definitely just do not have a command of this material to present it usefully, but thankfully it's the very last thing in the paper.
Maybe those were just exercises for the students.
Yeah, they might have been. For all I know, the students succeeded. They did pretty well. This is actually the end of my slides. I didn't make like a thanks slide or anything, so I will stop there. Maybe we can have like a little chat.
So you glossed over the load update pair section very quickly. Was that like an early definition of setters and getters?
Potentially. No, I wouldn't say. I guess it depends how you define setters and getters, but I think the loaded update pair was being defined in terms of L values, which I don't tend to think of like, say, an assignment to the variable x as being a setter. I guess it could be. It depends on how you define it, but I tend to think of like setters and getters as things one operates on sort of higher level data structures and not things that operate on, say, the simple table.
Okay. Most object-oriented languages, they're semantically equivalent. Like you define a assignment to be a set, and you define the function which manipulates that set, and same for get.
But most object-oriented languages also have like weird primitives that have independent sets of load update pairs that are not setters and getters, right? Like assigning floats to things.
Most is a fighting word.
Some. Ones that you don't like. But I think certainly like semantically I would say there's no more content in it than setters and getters. This is definitely a definition of that. I find this section weird. Maybe you have more insight into it. Like, it seems to me that everything in this section has already been said earlier in the context of L values, so it's not super clear why it happens, because it's not even that it's much more formal than the original presentation. So I sort of don't have a great insight into it, so maybe your perspective is actually way better than mine.
We can talk later, I'm sure there are more questions.
Okay, cool.
Maybe.
So you opened up saying that you don't like constructive mathematics, and then you gave a talk about programming language semantics. Like, how do you reconcile that?
Pretty simply, actually, which is like, I think programming languages are awesome, algorithm thinking is awesome, but I don't think that because it's awesome, we shouldn't have things that are non-algorithmic. Like, I don't think that the parts of math that are non-constructive are somehow invalid. Whereas I think like the hardcore constructivists would sort of argue that they're suspicious.
Is it a matter of degree?
Yeah.
Okay.
Yeah, I wish I understood this topic better. Sort of having read a bunch about constructive mathematics recently, sort of like things like the axiom of choice seem like things that constructive mathematicians are pretty uncool with, whereas they seem useful to me. I can't tell whether that X was like a straight edge X or like a hate axiom of choice X, but maybe both.
I have a question that's more about Julia used in the paper.
Sure.
Okay. How do you find Julia as a language for working in ML and data science?
I think it depends on what part of those things you care about. I think that it's really awesome at some of them and really bad at other parts. So I think, I recently realized like I should have, when I first got into Julia, I was doing a bunch of stuff that many people that I know who do data science don't do. This is actually a part of like, I especially like now that I work at like a big data science group, I've sort of started to realize sort of like how many different people call themselves data scientists who like have basically nothing in common and nothing to say to one another, which is like I was starting to do like a bunch of model fitting using stochastic gradient descent, and I think like that's a context in which Julia is really awesome. Like I just want to like fly through data in some file that's like maybe a terabyte in size and fix a model. Then Julia is awesome for that. It's awesome in the way that, say, C would be awesome, but arguably easier to write. I certainly find it easier to write. It's way better than, say, like Python or R would be for that. But actually, I think like a huge amount of the community that uses Python or R doesn't ever do that. I think they just don't think about, say, stochastic gradient descent. I think they think much more about, especially like, I think a lot of sort of like data science-y stuff, like pandas or dplyr or like modern stuff that's being built, I think of many of those things as like very much the like relational model, but being sort of built into our programming languages. And I think Julia, and I'm largely the person who can be blamed for this, has not done a great job. I think that there's just a lot of work that needs to be done there. In particular, I think the tools that have been used and the approaches that have been taken in both R and Python are not well suited to type inference. And so the result is that imitating them, which is what we started by doing, has given us solutions that are not great. They're not like, they're probably worse than R and Python, but they're not like crazy worse, but they're also like all of the things that I was excited about sort of haven't been achieved. And largely because we really need to like gut those things and use systems that have much more inferable types. So like an example, I wrote a blog post 6 months ago or whatever about like replacing the idea of NA with a whole type, a parametric type called nullable. This is like making missing this amenable to type inference. And right now, missing this in Julia just isn't amenable to type inference, it just breaks everything. And like when I say breaks, like it still runs, it just slow. And at which point you're like, well, I tried to write slow code already, so I didn't gain anything. I actually think this is like part of why, like reading these sort of programming language papers is like I think we're really still super far from having a good language for expressing data science or ML. Like I think the tools we have are either like really low level or really high level, and the high level tools are actually really bad at ever being fast. And the low level tools kind of suck. And I think we're pretty far still from figuring out all of them. I'm hopeful at least like sort of nullable will get us part of the way, but I think like getting nice tabular data representations, getting those kinds of operations is like a thing that really matters. And the last thing also is like, and this is going to be really heretical, but maybe people will find it fun. I personally think like everything that's not done in SQL, you should ask yourself why. Like SQL is super scalable, and we have awesome systems. I'm a huge fan of Presto, which is like a tool that Facebook has built. Hive, another one. Like those systems are just awesome. There are many things to complain about them, but they let you process more data than anyone has ever seen before using a really simple, clean programming design. And they sort of just solve all of these problems. And I actually think that like broadly, we actually haven't so far come up with any tool that's better than SQL so far. Like pretty severely so. Cool, that was a great question.
Yeah. Okay. Sorry. So I have a kind of artsy question here. You'll pardon me if I'm going to try to extend the metaphor too far. This is a little in the architectural nature of these things. Some people compare frameworks to the microkernel because of the way that it structures message passing, otherwise kind of organizes its day. And in that regard, compiler, an interpreter being the proxy of that, is kind of an extension then of the processor itself, whatever it's actually doing the core work. So, given that a framework is always going to extend out of, a language which is compiled, so the compiler itself, have you ever thought about that kind of architectural relationship between the way in which a language, its compiler structures operations efficiently and the kind of frameworks, or kernels, obviously they can extend out of that, how we might utilize that to develop, more efficient systems for, whether parallelizing or, distributing these operations that we're doing in the language across multiple systems.
So I've definitely thought about it. I don't know if my thoughts are that useful, but I'll tell you what I've thought about it.
Curious, that was the question.
Yeah, I think you will find that many people have a lot more interesting things to say about this than I do. But I think basically, like right now, my view is we sort of have two ways of thinking of computation. We basically have the way that actual computers work, which is the von Neumann model, and pretty clearly described in this. And then we have the totally pure, no von Neumann model, like don't even talk about the abstract store functional programming style. And I think that that style is really awesome for various types of parallelism, but it's like not done a great job. Probably gonna get lynched after saying this, but I think the functional programming language, I think my language community has done a lot of amazing stuff, and I think that in terms of like giving us frameworks for thinking about computation is giving us the most interesting new ones. But I think right now they have not done a good job of thinking about how to take control of scientific computing in like a viable way. Like I think they're not doing things that say like people at CERN really are going to care that much about. I mean, I'm sure there are people at CERN who use those languages, so like, don't get me wrong. But I think like there are still a huge amount of people, especially in science, who really care about the machine and want to get that last little bit out of the machine. In which case, like the language. Like the design of every language is sort of ultimately totally constrained by the fact that there are things machines are good at. So like things like Julie has thought a lot about lately about how you deal with SIMD. So like SIMD instructions, which is like a thing that modern machines are really good at, which we can operate quasi in parallel on a single core. How do we make sure that languages are good at exposing those things? And I think that the hardware architecture of our machines severely constrains us if we even talk about it. And as soon as we want to safely get away from that, we basically have to just stop talking completely about hardware, in which case we sometimes run risks. And I think this is sort of my take on sort of like the sort of functional programming and scientific computing is like they haven't quite figured out how to catch up with like hard-written like Haswell CPU code. For instance, one example, I don't think there's any awesome basic linear algebra system written in Haskell yet. Maybe one day it'll be there, but I think like we're not quite there. And I think that's sort of basically because there only are two frameworks right now we know about. There's sort of like one that doesn't talk about machines and one that talks about machines. The one that talks about machines tends to basically talks about x86 machines, like the current generation of x86 machines. All right, well, that's a sign. It's time to go. Cool, great. I guess.
So, that's a sign I shouldn't have the mic. So, somebody has to be a jerk. There's a lot of BS in economics, but I think Keynes and Hicks had plenty of insight. There's a throwaway comment.
I love economics. But to be clear, like I did a PhD in behavioral economics. My advisor was an economist. I love economics, but I also think that there is lots of BS. I mean, you haven't heard me talk about psychology yet, so maybe there's another side of this talk. But I do think, I will stand by my claim, which is sort of, I think there is a dangerous disposition to axiomatization without insight. There's even a paper I love about people's attitudes towards delayed reveals of uncertainty. It's a Krebs paper from the 70s. And this paper is amazing because it's written in Econometrica, an already heavily mathematical journal. And it's like, we assume that the readers in general will not be able to follow this paper. Just try to get the gist. And it's like, well, if all they're going to get is the gist, why even write them out? And this is like a topic that many economists, I think, you usually find economists who either like totally agree with me, which there are many of them, or they're like, oh God, you're a terrible person. And I think like there has been a dangerous tendency to like love formalism for formalism's sake in economics. Another good example is just sort of like contrasting physicist math with mathematicians' math. Like as an undergrad, I was a mathematician, and like I work with a lot of physicists now, and physicists do shit that's crazy. Like they just like make up stuff that's clearly not true, and yet like they get the right results, and it's awesome. And you're like, you guys are doing cool stuff, and I should do more of that because like often I get hung up on rigor in a way that's actually useless to me. And it's like part of what I love about this paper, and like I make fun of it, but I do sincerely believe that one of the crippling problems in modern economic theory is a tendency to prefer rigor over useful content. Or like, examples are like all of the sort of modern micro work on the attempts to like make behavioral economics into math. There's a lot of this work where they're like, well, I acknowledge that you don't follow probability theory, so what if I were to make a broken version of probability theory, axiomatize that, and see what would happen? And you're like, well, first of all, it can't be useful in practice, because it's not real probability theory. And then two, is it actually a valid description of people? And I would argue no. And so this is like where I would say like you wind up to this axiomatization. That's Keynes, though, awesome. Cool dudes. But it's like also like lots of Samuelson, also awesome. I mean, like one of the things that's awesome if you read Samuelson papers, and Samuelson is certainly, there's no doubt in my mind that Samuelson is the person who was guilty of creating the modern mathematical economic movement. But Samuelson himself is always kind of like, I'm just making this stuff up, guys. Let's be clear about it. And then 60 years later, people forget that. Like actually, so for instance, my thesis is about exactly this, which is Samuelson made up this idea of exponential discounting as a way of thinking about the future. And he's just like, oh, this is totally made up. And then people like started assuming it, and then like wound up to a point where people were like, well, not only is it assumed, it's like the only morally defensible way to think about the world. And then like, I think you do really run a real risk of this. I pick on them. You could find many fields that I would pick on about this exact point. I think that's part of why Strachey is saying it. It's like, there's a very severe disposition among many people who are mathematicians towards axiomatization.
You scared us all.
Awesome. I'll leave on that note.